we have a question. We are given a number. We have to count number of set bits. So what are set bits? We know that this number is in base 10. Okay, the normal numbers are in base 10. So if we represent this number in binary format, what would this number be like? It is 4 plus 2, that means 0 1 1. It would be the binary format for this number, and for 8 it would be 1 0 0 0. This would be the binary representation of 8. So we have to count the set bits. So what are set bits? The number of ones bit are called set bits. So I write it somewhere. Number of set bits are called number of ones bit. Ones bits are called set bits. Set bits. So we have to calculate the number of set bits in the binary representation of the given number. So I think it would be an easy task if we know how to convert a decimal number to binary. So this is a decimal number. If we know how to convert n equals to 6 in its binary representation, that would be 110. And from this binary representation, we can easily count the number of ones bit. So it would be a easy task for us. So we can easily convert this decimal number to a binary number, because what we have to do basically, if a number is given to us and modulo by 2, what will be its modulo? It would be 0, and we divide this number by 2 again, so this would be 3. Again modulo by 2, it would be 1, and divide by 2, it would be 1. Okay, so 6 mod divided by 2 is equals to 3. 3 divided by 2 equals to 1. 1 mod 2 equals to 1. So we look at the binary representation from bottom to up. So the binary representation of 6 would be 1, 1 and 0. Let us analyze it for 8 also. N equals to 8. What we'll do, we have 8, take the modulo by 2, it would be 0, and we divide 8 by 2, it would be 4. Again we take modulo by 2, it would be 0, and divide 4 by 2, it would be 2. Again take modulo by 2, it would be 0, and again divide 2 by 2, it would be 1. Again we take 1 mod 2, it would be 1, and divide 1 by 2, it would be 0. So we end this process when our number reaches 0. Okay, so as we can see, the representation, the binary representation, we evaluate with bottom to top, so it would be 1000, and this is what the binary representation of 8. So we have find the process how to find the binary representation of a given number. Now we have to find the number of set bits, so we can easily iterate over this binary representation that would be in a string format. We'll take a temporary string to store this binary representation and iterate over this and find the number of set bits or ones bit. So in this process, how much time complexity we require? We require time complexity log n to change this decimal representation to binary representation. So log base 2n for this, plus to iterate over the binary representation. To iterate over the binary representation, we require order of n, nahi, we require how much time, because n would be 8. So if you look at the binary representation of it, it would be uh, 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 one thing, if we take the binary representation of this number, it would be 3. So how many times, let's suppose this loop runs k time, or we can say it runs log base 2n time. So these many numbers are available in the string, and we have to iterate over this string. So how much time complexity we will be requiring? We will be requiring approx log base 2n time complexity. Because again we look at this, what is log base 2 6? We look at it as 1 2 3 3 steps. This is what we are getting. We are getting 3 steps. For log base 2 8, it would be 3. So we are just iterating over it. Log base 2n plus 1, the 4 bit we are traversing, so we can take an estimate as log base 2n. So the time complexity would be twice of log base 2n. Okay, and space complexity would be order of log base 2n, because basically what we are doing, we are storing these many numbers of bits in a temporary string. So for the temporary string we require this space. Okay, so I can write it clearly that the time complexity would be order of log base 2n, and the space complexity should be order of log base 2n. Is this correct? Let us analyze it. So we have our question here. So the time complexity is correct, but the space complexity is exceeding. So we have to try another method so that we can solve this question. Okay, we have to try out one another method to solve this question. So let us try out. So basically, if we have the binary representation, let's suppose, what is the binary representation of 6? 1 1 0. So let me erase this part. 1 1 0 is the binary representation of this. Now the number of set bit in this are 2. So what technique we're gonna apply is, we're gonna find the rightmost set bit. Rightmost set bit, what is the rightmost set bit? It is the rightmost ones bit. It is the ones bit from the right hand side. Okay, ones bit from the right hand side. So what we are doing, we are having a number, we end it with a number this. So what we are just trying to do here, let me just do a simple thing. This is a binary representation of the number. Okay, now we have to count number of set bits. So what we are doing, we are calculating this, the rightmost set bit. And what we are doing after calculating, we are keeping our counter, and whenever we find a rightmost set bit, we subtract that bit value from the given value. Let's suppose the value of this, what we are given, n equals to 6, and the rightmost set bit we are getting is the second position. And what we'll do, we'll make all the bit null, all the bit 0 except the rightmost set bit, it would be 1. And if we subtract this value from this, what we are getting, we are getting 110, that would be 6, and it would be 2, we are getting 4. So basically what we are getting, this one. And again, when we find the rightmost set bit, it would be this one, and if we subtract this from this, we'll get 0. We keep a counter until our n value has reached 0. So what I am trying to say is that Let's suppose n equals to 25. Now, to calculate the binary value for it, we can use the same formula. No, same formula not. What we'll do, we'll calculate 16 plus 9, simple thing. 16 plus 9, and 9 will get 8 plus 1. So we have 1 2's bit will be 0, 4's 1 value will be 0, 8 will be 1, 16 will be 1. So this would be binary representation 1 1 0 0 1. Okay, this would be the binary representation. Now what we are trying to do, we are just trying to find the rightmost set bit value. The rightmost set bit in this collection of bit is 0001. Okay, and after calculating it, we keeping a counter. If we have found the rightmost, until our number has reached 0, we until our number has 0, we do such thing. We calculate the rightmost set bit, we subtract it from the given value. After subtracting, it would be this. After subtracting, it would be this, and we do this process until this bit values will be 0. Okay, so we have 11000. We again found the rightmost set bit value. It would be 10000. We subtract it from it, so it would be 0 1. Okay, it would be this. We are keeping a count. It would be 2. Now again we check if the number has reached 0. No, it hasn't reached 0. We calculate the rightmost set bit. We again subtract it from the given. We increase our counter, and now our n value would be 0. We stop our loop. So the number of set bit in the number 25 are 3. Is that so? Yes. It is. So how would we implement this? Simply, we are given an integer end. Okay. From this, how can we analyze it? Let's suppose we are taking input from the user. So until we also have to take the number of, take a counter so that we can count the number of set bits. Initially it would be 0, and we have our n value. If n not equals to 0, we're gonna use this loop. What we're gonna do, we're gonna calculate the rightmost set bit value. How can it be, how can it be calculated? We do n and minus n. So we perform n and minus n. It would give us rightmost set bit value. And how it would give us rightmost set bit value? So let's suppose the given value is this one. So the minus 1, how can we calculate the bit value for this one? We take the 2's complement method. Okay, 2's complement method. What we'll do, uh, first we take negation, and second we add one bit. So what we have this one. We take just the negation of it. So the bit would be this, and add one to it. So it would be 0 0 0 and 1. So it would be this one. And if we take and of this one and this one, it would be this one only. So the rightmost set bit value would be this one. So we can analyze now. If we subtract this from this, we get our n value as 0. Let me take a bigger example, n equals to 25, to make it more explicitly clear. What the bit value we have get? We have a 16 plus 9, that is 8 plus 1. We have our 1. 2 bit will be 0, 4 bit will be 0, 8 bit will be 1, 16 bit will be 1. We have this one. We have to calculate the number of set bits. Okay, this easy task we have to perform. We have find one method to calculate, to find the binary representation of the given number. and iterate over the string that stores the binary representation of the given number and find the number of set bits. That is the task, that is the childish task we can do. Another thing what we can do is use our mind to find the rightmost bit, rightmost set bit and subtracted it from the given value, because basically the values, because the value of a given number would be basically because of the ones bit. And what we're gonna do, we're gonna find the rightmost set bit. Okay, ठीक है. Now, how can we? I have told you that rightmost set bit can you found out by taking and n minus n. So we know the binary representation of n. So how can we know the binary representation of minus n? What we can do, simply, how can you find the binary representation of the negative number? We take the negation of the n representation and add 1 to it. This method is called 2's complement method. This method is called 2's complement method, in which we take the negation of the given bit representation and add 1 to it. Okay, so this one would be 0, 0, 1, 1, 0 plus 1 we added to it. So our value would be 1, 1, 1, 0, 0. And we take the end of 1, 1, 0, 0, 1 and 0, 0, 1, 1, 1. We take the negation of it, it would be, this one would be 0, 0, 0, 0 and it would be 1. And if we have made a counter would be 1, and we subtract the given value, the given bit value 1, 1, 0, 0, 1 minus 0, 0, 0, 0, 1. We subtracted, what will be the value? 0, 0, 0, 1. Again, our n value hasn't reached 0. Count is equals to 1. We again count the rightmost set bit value for this binary representation. So what would be it? So we'll take the negation 0, 0, 1, 1, 1 and add 1 to it. 1, sorry, 0, 0, 0, 1, 0. It would be the representation. We take the end value of it to be 0, 0, 0, 1, 0. Okay, so it would be it. So we have 1, 1, 0, 0, 0 and we have calculated. Okay, so this would be the representation. We increase our count and our value would be 0, 1, 0, 0, 0. Any doubts? 0, 0, 0, we take end of it now, we subtract it, so we have 0, we have 1. So this is the remaining bit. We again check, is our n value has reached 0? No, it hasn't reached 0. So what we can do, we again calculate the rightmost set bit value for this. So it would be this one only. We end it, sorry, we subtracted 0, 0, 0, 0. Count would be 3, and now our n value has reached 0 and we return the count. So I don't think I have a need to write the code for it, but if somebody want to understand it more clearly, if anybody does not get the approach I have used for them, I am writing this code. I have an n value, I have taken, so while n value hasn't reached 0, what we can do, we calculated rightmost set bit. Okay, that is n minus n. Okay, rightmost set bit value I have calculated. Now what I have to do, I have to increase our count by 1 and subtract the n is equals to n minus rs. Okay, and at the end we will return the. So this is just the code, and how much time this would take. to learn. It will take just the order of log base 2 and time, and a time complexity and a space complexity of order of 1. So this is a fucking good question to enhance your bit manipulation skills. Okay, so